Hey guys, hope you're doing good. So today I want us to talk about optimization. And as you can see from this text, optimization is usually the idea of making the most effective use of a situation, most effective use of your time, of your resources, of your facilities. And that's a very important idea or skill for businesses. Mathematics or inequalities that we're studying right now, linear inequalities, can help a lot with optimization, and they're used today a lot in the world to solve practical optimization problems. Let's start with a simple example that can be relatable to you guys. Let's imagine a situation where a friendly neighbor called Zoe wants to go to a supermarket and buy some pencils and erasers. Okay, so this is what we know. Zoe wants to buy pencils and erasers. We know that Zoe wants to have at most 5 items. At most 5 items. At most 5 items means that she can't buy more than 5 items. The total number of items she can buy is 5. We also know that Zoe only has 1,000 shillings, unfortunately. This doesn't mean that Zoe is not a rich person. She's very rich. Just using 1,000 for simplicity. But we know Zoe is a super rich person. So she has 1,000 shillings. She wants to buy a maximum of 5 items. And the other information we know from this supermarket is that pencils cost 500 shillings. Pencils cost 500 shillings and erasers cost 200 shillings. So pencils cost 500 shillings. Right handwriting. Pencils cost 500 shillings and erasers cost 200 shillings. 200 shillings. So, simple question. What are the possible combinations of pencils and erasers that Zoe can get from this supermarket? So if I call the pencils X and I call the erasers Y, what are the possible combinations that she can get? Well, let's find out. The only conditions are that she has to buy not more than 5 items, and she has to spend not more than 1,000 shillings. Those are the only conditions. So she could go to the supermarket and get none of each. She says, I don't want to buy anything. That would be fine because that satisfies the conditions. She could go to the supermarket, get one of each. That satisfies the conditions. She could get 0 of pencils, 1 of erasers. She could get 2 pencils, 0 erasers. I hope you can see that there are many possible combinations. Let's continue the table here. She could get 0 pencils, 5 erasers. She could get, there's so many different possible combinations. She could get 1 pencil, 2 erasers. She could get 0 pencils, 4 erasers. So as long as each of these combinations that I'm thinking about satisfies these conditions, condition 1, that the total of the 2 items bought is not more than 5, and condition 2, that the total amount of money spent is not more than 1,000, then we're good to go. If you look at each of these conditions, if you look at each of these that I've written down, this would only cost her 0 shillings. This would cost her 700 shillings. This would cost her 200 shillings because this is 500 and that is 200. This would cost her 1,000 shillings. This would cost her 1,000 shillings. This would cost her 500 plus 400 is 900 shillings. This would cost her 800 shillings. So as long as I'm satisfying these conditions that have been given in the question, as long as I'm not buying more than 5 items, and as long as I'm spending less than 1,000 shillings, I'm satisfying the conditions for this the Zoe problem. So this is the idea of optimization. If you're helping someone run their business and you're trying to figure out what are the possible things you can do to optimize costs, This is what it looks like. Now, how can mathematics help us to have a more elegant solution? So, if I try to think of this mathematically, if I call the pencils X and the erasers Y, I've been told she can't buy more than a total of 5 items. And since pencils cost 500 and erasers cost 200, I have also been told that she only has 1,000 shillings to spend. Now, I have not been told anything else besides this, but I know that Zoe cannot go to the supermarket and buy -2 pencils, if that makes sense, because you can't have negative pencils or negative erasers. So in other words, whatever happens, she can either get 0 or more than 0. She can either get 0 or more than 0 pencils, 0 or more than 0 erasers. If you want, just for kicks, you can also say she cannot have more than 5 pencils. She cannot have more than 5 erasers, if you want, but you don't have to. So we can use Desmos to try to see what the solution to this would be. So the only thing I'll do would be go to Desmos. And when I go to Desmos, I type in my equations. First equation is x plus y x plus y x plus y is less or equal to 5. That's the first equation. Now something that I want to teach you for today is I can restrict the range of an equation on Desmos. If you look at that equation, it's going beyond 5 and it's even going into the negatives. If you can see it this way, it's going into the negatives. But since I know that whatever I'm dealing with is greater than 5, I can restrict the how far this goes. So I can restrict x. Because I know x is greater than 0, I'm going to add that this is a restriction for the values of x of this graph. It's simply telling Desmos not to show me anything that's less than 0. So that's why initially there was all the shading before, in the negatives, but it's now gone because I've put that restriction. The second restriction I'm going to put is y is also greater than 0. That's the second restriction I'm going to put. So like I said before, I initially had I had red shadings below the 0 axis, but since I'm only interested in things that are greater than 0, it cuts that off. The second equation is 500x plus 200y is less or equal to 1000. That's the second equation. Again, I can restrict the range and domain. I can restrict the range and domain and say x. I'm only interested in x values that are greater than 0. So it shows me that. And I'm only interested in y values that are greater than 0 for this equation. So I'm telling it that for this equation, I'm only interested in x values greater than 0 and y values greater than 0. If you really want, you can add on this same line. If I wanted, I could have written, because remember I said x can also be less than 5, y can be less than 5. If I wanted, I could have restricted x to be x values between 0 and 5. Between 0 and 5. That doesn't make much of a difference. So yeah, if you wanted, you could have done that. I'll tell you more about this as we do more things on Desmos. But for now, let's just use these restrictions. X is greater than 0, y is greater than 0. Now I have a neat graph. It's nice and neat. And remember, I'm interested in the region that's satisfied by both of these inequalities. The first section right here, this first section is of the graph. So the red section and the blue section both intersect nicely in this little triangle here. Why isn't it selecting? This little triangle from 0 to 2 to, up there at 5. So they're intersecting in that region, and the distinctive points in that region, are going to be my solutions to this optimization problem. So now I know all the solutions to this optimization problem. I can just read off the coordinate points. I hope you can see my cursor. I can just read off the coordinate points in this optimization problem. I go to each of the points and read them off and put them in a table, and those are going to be the solutions to this Zoe problem. So I'll draw a table of x and y, and then I'll go to the graph and look for each of the points. If I look at this graph, 0, 0 is a solution, 1, 0 is a solution, 2, 0 is a solution. All of those points are solutions. Pause. How do I pause? Yeah, so like I was telling you, I've tried to label the points, and I hope you can see them now. The distinctive coordinate points, each of those points that you can see is a solution to this optimization problem. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 possible solutions to this optimization problem, and we've been able to see that because we used some mathematics. When I tried to eyeball it here, I only came up with 1, 2, 3, 4, 5, 6, 7 solutions. So that's how math helps us with optimization. It's really easy. The idea is easy. Let me just do one example. This delivery truck company, I'm going to help you find the equations, then you can do the work on Desmos. This truck company has two types of trucks, A and B. We can see in this question A and B. A and B total is 20. So let me say A is X and B is Y. The total of the trucks is 20. There's no way they can use more than 20 trucks to do a job because they only have 20 trucks. Okay, what else do we know? Truck A can only carry 20 tons per trip. Truck B can carry 30 tons per trip. This can carry 20 tons. This can carry 30 tons. And altogether they need to do a job that's carrying 1,000 tons, right? These are the equations. These are the primary equations that you need to take to Desmos and try to solve the problem. But you also know definitely that x has to be greater than 0 and y has to be greater than 0. And just in case you're interested, two other equations can be x has to be less than 20, and y individually has to be less than 20. But these last two you don't actually need them. So yeah, those are the equations you need. Take them to Desmos. After you take them to Desmos, draw the graphs and look for the intersection of the wanted regions, and then find the solutions. You put them in a table. So yeah, I'll post this one for you guys to do on your own. That's about it.